To all. It gives me immense pleasure to introduce our resource person, Dr. Manivannan R., scientist, Wire Arc Additive Manufacturing and 3D Printing, Center for Additive Manufacturing and Metrology Group, CMERI. Dr. Manivannan R. is a mechanical engineer with specialization in manufacturing. He did his graduation and post-graduation at Anna University and pursued his postdoctoral degree at IIT Bombay. He is an ad hoc faculty in NIT Trichy. He has published more than 10 papers in international journals and more than 15 papers in national journals. He has also contributed in more than 25 workshops. His core area of research is metal-based additive manufacturing process. We are really gifted to have such a distinguished person with us today. Thank you.
Thank you, sir. I now invite Dr. Manivannan R., scientist, Wire Arc Additive Manufacturing and 3D Printing, Center for Additive Manufacturing and Metrology Group, CMERI, to take over the session.
Thank you for the introduction. Hello, thank you for the introduction.
Welcome, sir. Welcome, sir.
Yeah, I think we can right now, we can go with our presentation.
Yeah, please.
I hope the presentation is available. Can you see the presentation?
Yeah, it's visible, sir.
Yeah, okay. Actually, it's first of all, thank you for everybody. It's for the nice opportunity for me to interact with our people. This time I'm planning to give a small kind of brief introduction about pre-processing and post-processing in additive manufacturing. Mostly I'm working in metal-based additive manufacturing. So most of my thoughts are oriented towards metal-based additive manufacturing because there are, I think you people know, there are plastic-based, ceramic-based, so this ice-based, foam-based. So there are several forms of additive manufacturing. So here I am a pure metal guy. So I am discussing things about metal-based additive manufacturing. Before getting into this webinar, I just want to introduce some facilities available in CSIR CMERI. Actually, CSIR CMERI is a central lab located in Durgapur, West Bengal. So here we are handling both metal-based and plastic-based, means thermosetting plastic or this PLA, ABS, this type of plastic also we are using. So this facility, like actually we are using Stratasys Object 260 Connect 3 is a machine we are using. We are having here. And if you come to metal, there are two forms of metal, means wire-based additive manufacturing and another one is powder-based additive manufacturing. So we are handling powder-based things, means like 316 stainless steel powders, using laser as a source for melting. So these facilities also we are having, and even we are using wire arc additive manufacturing, means like wire form of feeds. So almost we are covering all the facilities that is used for research and development basis. Even the students belongs to, means or the faculty, they want to do their research in this area, they can go ahead with this type of facility that we achieved through our wire arc additive manufacturing process. The only difference with powder and wire is, with powder you can go with small components, means like tooth implants or medical things like that. But when it comes to wire arc additive manufacturing, you can go for a even meter size component, means very big component. So this is the major advantage of wire and powder. So we are handling both the things. It is not like even we are using thermoplastic, thermosetting plastic, all these things we are using. So this is the facility available in CSIR CMERI, based central government organization. Now I will get into this topic. Actually, if you consider a wire arc additive manufacturing system, means how the wire arc system looks like, means actually it is not a separate equipment like normal CNC machines like that. So wire arc system includes different parameters, means it has a process control system and process monitoring system. So first of all, I will start from It's a CAD modeling software. Means actually in CAD modeling, like SolidWorks or Pro E, we are developing the component. That component will be imported for 3D slicing. Then this 3D slicing will be given to the path planning strategy, how to do the path planning. Then it will feed it to the process planning, process control system. The process control system, there are different things out there actually. Gentlemen, I'm audible. Hello.
Yes,
Yes,
sir.
sir. Yes, sir.
Okay.
You're audible, sir. Yes, sir.
Okay, thank you. Actually, in this process control system, there are different power sources. Means arc is a power source, plasma is a power source, laser is a power source, electron beam is a power source. Actually, see, when we are melting the material, heat is the input for melting the material. So the material is the heat source is from arc, plasma, or laser, or electron beam. So this is the power source. Then the positioner. Positioner is where we are depositing, means the X, Y, Z coordinates, so nothing but. So these are position. So these are process controls. From that, you can see the image. It shows you the exact robo is handling, means robo is attached with the welding torch that used for deposition of the material, and you can get the data. So now, actually, in our before designing this, means before starting the deposition, we will give some signals for means if it's a welding system, we will say voltage and power, sorry, voltage and current to set the bead parameter. But what bead we are obtaining, that we don't know. Means after deposition only we came to know that. It may deviate from the original data to the error data. So what we are doing, we are taking the feedback from the system like welding signal, means arc voltage stabilizer, means how long the arc is maintaining, charge coupled device camera, IR pyrometer, means for measuring the temperature, laser scanner. Actually, it is a laser scanner is a single point height measurement system, so that it will tell you the what is height. So all this data, it means actually what is happening here in this power, means you gave some power to the system to operate. The welding signal will recheck or correct whether the power given will be obtained or not, means whether the input and output are same. If the input and outputs are not same, this will give the feedback to the power, either increase or decrease to match the input output power. Charged coupled device is a camera. It is exactly like what we are seeing, means through naked eyes. So through naked eyes, we will see whether it is good or not. So this thing will be done by image processing software. For that, CCD camera will take the image. That image will be compared with the previous standard data. Then it will give you the output whether what parameter can be corrected or not. Then IR pyrometer. This is for temperature. So when we are doing deposition, means additive manufacturing process, this the temperature of the welding around 1200 degrees Celsius. So this during this time, you cannot deposit the molten metal over the molten metal. We have to give some ideal time or for deposition strategy. So this IR pyrometer is used for maintaining the dual time of the weld. So this will measure. So laser scanner ensures the physical characters like what is the height, what is the width, means what is available in the geometrical characters. That will ensure the laser scanner. So after taking all this feedback, the process monitoring system will enable whether we are doing in a correct way or is there any mistake in the process system. If there any process error, then it will go for bead modeling, means again it will recreate, means the adjustments based on the feedback, it will do the bead modeling. So something is wrong or something is mismatching, how to correct it. After that, again it will go for path replanning, because if you come to area filling, one corner to other corner, if you are going, means if you take 10 mm square, if it is covering 10 mm by 1 mm length, if it is the bead is not sufficient, it has to repeat it for the 0.5 mm like that. So this replanning will be done here, and the process control, means after completing all these things, again we are migrating to the process control system. So this is a kind of closed loop system. So if CMER is having this WAAM system as a closed loop, actually we are working with some 3 robots all together. We can, so that in a single go we can go up to some 6 meter to 8 meters of component. Means it's ideally we can say for the thermal applications or marine applications or aerospace applications like that. Right now we are working for aero systems, means this Tejas Airlines some valves. So this is going on in these things. Now, how the additive manufacturing, means wire arc additive manufacturing system looks like. Previously, we discussed the schematic setup. Now I'll come to the workflow. First is design. Means design is based on the requirement of the consumer, means what type of work they want or what type of component they want. Then pre-processing. Pre-processing is before doing what are the things before deposition, means printing, what are the things we are doing is a pre-processing. Post-processing, after printing, what we are doing is post-processing. So all together will ensure the quality of the component. First, I will come to the pre-processing. Right now we got generally we will use step file. Before deposition, we got a step file. So it has 2 things. But before going for deposition, we have to understand 2 things in a software manner. One is slicer, another one is toolpath. Means with this only we can progress in the next slide. What is slicer? Can you see the slide? This is slicer. What happened? Actually, here these vegetables are sliced, diced. So what is the thing? Slicer means we are making n number of slices. Why we are making slices? Because we are depositing the component in layer by layer manner. If you assume you are going to deposit 100 mm component, means 100 mm height component. If you sliced it into 1 mm, 1 mm, you have to repeat the process for 100 times. So in case when I'm using wire arc additive manufacturing process, my wire diameter itself 1.2 mm. So obviously I'll get more than 2 mm of slicing. In that situation, my slicing will be 2 mm. So I have to repeat the process for 50 times. Then only I can go to the 100 mm layer. When you are using this micron machines, powder based machines, the powder diameter itself 60 to 100 micron diameter. So if it is 60 to 100 micron diameter, means if you assume 100 micron diameter, for reaching 1 mm, you have to repeat the process for 10 times. So the slicer, it will help you to understand how much layer thickness has to be given to the equipment, means any equipment, means even it's a plastic based machine or metal based machine or any machine, it gives the what is the number of layers. And there is a trick in this. Actually, what we will say, if you go for fine layers, the staircase effect. Actually, if you see this left side image, both are dome, but it's look like a staircase. But if in the right side, it is completely like a dome shape, means it's like a cylinder shape. Why? Because if you give the maximum number of slice, then you will get the staircase effect. But if you reduce the thickness of the layer slice, you will get the uniform surface. This is the difference. So this slicer is important in pre-processing. This ideally depends upon the equipment. And actually we are for transferring file, we are using STL format. I think almost all the guys knows about this STL format. Why? Because this is a standard, and the main advantage with the standard, this STL format is there is no loss of data. Actually, it gives 100% data. Only it will never represent the color or texture, only the data. So they are saying it is a standard triangle language, a standard tessellation language. So the STL file is commonly used, or step file. Now I'll come to the slicing types. First one we saw was slicer. In this, we are seeing how the slicing types are happening. Actually, I hear. Hello? Any doubt?
No, sir.
Okay.
You can continue.
Yeah. before when you are saying slicing, I showed in the previous structure, it's all uniform, just like all dimensions are same. It's like same thickness like that. But when it comes to slicing time, see the slide I am showing, I diced the vegetables as a kind of slicing types. So why this slicing types matters? When you are depositing the component, there are axis symmetry components or complex geometries. If it's axis symmetry components, we can go for uniform slices. Actually, right now, maximum components are going in uniform slices because like it is kind of the practiced one. There is another kind of thing called non-uniform slices. When you are depositing a single component, let me show you one picture. Can you see the Y image? Means in the picture, there is a bottom corner left, there is a Y-shaped structure was there. In that Y-shaped structure, now if you take this right side, it was kind of uniform axis symmetry. But if it is like it is not axis symmetry or complex, when the stress is acting on the non-axis symmetry component, the stress will vary. Because it is not axis symmetry. So to contribute or to manage the stress accumulation on the non-symmetric component, we are going with this type of non-uniform slicing strategy. So these things will come into picture once we are getting some experience or after working on some area, we can get this. The same will be applied for complex geometries also, complex slices, whether you can go for uniform slices and non-uniform slices. These are purely depends upon the engineer's knowledge, means where we can go for uniform slices, where you can go for non-uniform slices, and how to provide the support, all these things are depends on them. Then finally tool path. So tool path is like means you are depositing a square of, if you assume 10 mm to 10 mm, means just a 1 mm 1 centimeter cube. So you have to fill the complete area. Means how we will fill? Means either we can go from left to right, right to left, or you can go from the conformal area as I showed in the figure. So these are the things. What will happen if you go with continuously left to right? The heat accumulation will be always in the one corner. So this will deteriorate the quality of the geometrical characters of the component. So what we have to do, we have to do some heat management system. Means we have to analyze how the temperature is playing a key role. See, in additive manufacturing, we are playing with the temperature. Means always the melt pool is there. So this is repeated heat cycles. So if you do heat cycles again and again, there is a accumulated stress will happen. So you have to concentrate how to design the tool path so that the heat will be uniformly distributed among all the parts of the component. So what I showed you in the slide is just 3 common type. Beyond that, there are several types are there. Means tool path itself a big research area. People are working on this to how to identify the uniform heat distribution in this tool path. So this is a common thing. And finally, this is orientation. Majorly, the shapes are either square or cylinder. Means this is the common shape. So you can keep the orientation. This is also again important because when you are starting depositing your component, you should know which orientation, which load, or how to keep it. Means how to give the support, or in all other parameters has to be managed. So this is the common shape. This is the common maximum available orientation can be adapted for deposition. Just go to the slide. Go through the slide. So up to this, we are discussing about the things what as a designer can be sit and do into the computer system. So after that, that's after completing all this idea of slicing and tool path, then we have to come to the equipment. Means physical pre-processing. Means physical pre-processing is nothing but means what we are doing before deposition in the machine. So first is we are loading and aligning the build plate. Actually, in additive manufacturing, everything is start with the base plate or build plate or substrate. So the thing is we have to keep the base plate ready. It should be dimensionally stable. And the thing is, we have to heat the base plate for up to some 300 to 400 degrees Celsius based upon the metal we are going to deposit. So why? Because if your base plate is under room temperature, if you assume that your room temperature is around 30 to 40 degrees Celsius, you are going to deposit a material of stainless steel. It is melting point, means its melting point is around 1200 Celsius to 1400 Celsius degrees Celsius. Now you imagine if your base plate is exposed to 30 degree to 40 degree to 1200 degrees Celsius, there's a vast difference in the temperature. This temperature affects the base plate and the heat distribution. So you will get the low quality, means deteriorated quality bead. So this have to be taken care, means the base plate should be heated up. And the temperature, means the atmosphere. Atmosphere plays a major role in welding, because if you deposit aluminum or this titanium, it is immediately it will be affected by oxygen. So this atmosphere has to be taken carefully. And preparing the loading stock, means feedstock. Generally, feedstock means if you take wire machining, wire or additive manufacturing, we will say wire means welding wire is electrode, and if you take this powder based machining, metal powder is a feedstock. I will explain you what is the difference between wire and powder, how to handle the powder. Actually, if you take material cost, means if you take powder, if a normal MS powder, just what we are using for the normal roadside welding wires, that wire is costing around 3000 to 5000 for 15 kgs. But if you buy 1 kg of MS powder, 1 kg, it costs 10,000, means 8,000 to 10,000. So the cost when it comes to this powder, it is so costly, means higher than the wire form. Then print speed and resolution. If you go with powder, earlier I said the powder diameter is maximum to 60 to 100 micron. So it means each slice diameter, means layer thickness is maximum 90 microns. So you can get the good quality of good resolution of the component. But in wire, the diameter is 1.2 micron, so 1.2 mm. If it is 1.2 mm, obviously the filling will be more than 2 mm. So you will get the 2 mm of waviness in the component. The quality actually, the integral part or the microstructure part of both the components are same, because both are operating under the same conditions. But in the surface wise, powder giving a fine quality, means that staircase effect can be nullified, but in wire arc the staircase effect will be there. Safety, actually there is a small problem with handling this powder, because when it is actually if you are using powder, there is a possibility of dust clouds. That dust cloud may be explosive, but in this condition wire is not nothing, like we can store in normal places, there is no problem in handling. And when you are handling this powder, when you are sneezing at this type of time, this powder you can inhale in your so these are creating some issue with the health issues. So these are the problem. And comes to manufacturing challenges, manufacturing of this powder requires huge cost, while the wire drawing is a wire drawing operations. So it is comparably easy and well established process. So these are the feedstock handling. So when you are going with this wire spool, there is no much precautions. Means like it is already came in the binded shape. So you can already it is used and it is well proven. We can easily use in any form. Any wire is available for deposition. We can, means any wire is available for welding can be used for deposition. So up to this pre-processing is completed. Now we will enter into the next domain of post-processing. Actually, people thinking additive manufacturing is deposition is important, or machine is laser or wire arc or whatever is important. They are thinking like that, but it is not the case. Actually, it was mentioned by John Burns that the battle is won or lost is post-processing, because you can deposit any component through this process, but whether the component is able to serve the purpose. If it is able to serve the purpose, then it is the battle is won. If the component is failed, there is no use of all your hard work. So that's why always post processing is expensive and it's time consuming than the printing itself. Because before that, what we discussed is just program. If you say 100 layers, one layer equal to 10 minutes. So 100 layers into 100 minutes, like that, we can take the things in a normal way. But when it comes to this post processing, it is not like that. It is actually consuming more time than the printing time itself. As I heard from the audience, there are faculty members are available for doing research. So I am trying to introduce some post-processing research areas, so they can use this type of things for their research. Actually, I'll show you some images. I'll discuss in the end slide. Post-processing. So what are the post-processing things? One is build removal. Actually, initially I said we are doing on the base plate. So if it is on the base plate, it must be removed. So how we are removing? And part separation. Sometimes we are building one component over another. It means stacking of component. Debinding and sintering for plastic first thing or ceramic based thing. Machining, surface finishing, heat treatment, residual stress. I will get into one by one. So build removal. I'm showing for this powder based thing. So in a powder thing, if you deposit the component, you have to remove from the build. Actually, there are a lot of powder will be in the bed than the component. That has to be removed carefully by vacuum cleaner, vacuum suction cleaner, like that, and separating from by either cutting through wire EDM or AXA or a bandsaw, like that. You have to cut and remove the supports and the base plate. In case nested component, if you build one component or another, means in sometimes in the teeth, when they are making teeth implants, they will stack one teeth over another teeth like that. So they want to reduce the cycle time. So at that type of times, they has to remove each single teeth from one part to another. So that is another thing. So debinding and sintering is generally they will use for binder based ceramic machines or PLA machines. What they will do, they will put it in the ultrasonic baths. Sometimes the surface will be not good. Actually, they will go for coating or painting, and these are the things generally they will go for debinding things. Machining, as like you are casting, our additive manufacturing also give near net shape. So for some particular applications like drilling or matting surfaces, we have to go for machining. These are secondary operations. Surface finishing, we have to go for the actually, as I said, you just see the top corner image in the right side top corner image. Wherever the laser beam spots, only that material melts. The other sides are not melted. So if you assume, if you take a powder as egg, means a normal egg, I mean a magnificence I'm saying, if in the egg the only one corner is laser beam spots, that part only melts and attached to the another part. The remaining major area is not covered. So what will happen? That will attach because of the minimum force, and it will be in the surface, it will deteriorating surface. When you are going this type of vibratory finisher or short peening or polish, it will, that extra portion will be removed. The down part is like it's a bath. So when the vibratory surface is removed, the sharp corners, all these things will be removed slowly. So these are the way to remove the surface finishing. Now I will come to the things called residual stress. So before when we are doing n number or repeated number of heat cycles, there is a thermal gradient formed in the component. It will affect the microstructure. This will accumulate the stress. That stress has to be removed. Then only the component can be it has more life cycle. So from here, I am trying to cover some research areas. It means people never attempted many areas to do these things. So first one is heat treatment. The first process for actually right now many researches in additive manufacturing is going on. for heat treatment, because we studied many heat treatment process, annealing, quenching, all these things. People are doing age hardening. This will help them to reduce the stress of the component. So this is one type of thing is going on. One is they are doing it furnace sintering and our HIP. So actually HIP is costliest process. So this is one type of process. Actually this is a schematic. Why I am showing here, from this slide, I am going to discuss about the post-processing methods only for wire arc additive manufacturing. So you can able to please see this slide. From there you have to imagine all the slides. This is a substrate. I build a wall shape, means a component is a wall shape. The new layer is deposition, the molten pool, the torch, and the arc is from the side. Can you see this? Means the filler wire. Now I will come to this. This is a one type of process, cold rolling process. In this, what they are doing, after deposition of this wall, they will make a roller that will roll over the weld bead with some load that will make the bead to be perfect. Actually, when we are normal metal processing technology, we are using hot rolling process and cold rolling process. I think you may remember this. The seed drawing is a cold rolling or a hot rolled plate or cold rolled plate. The same thing they are doing in the bead. So, hello. So this will help to get uniformity in the beads, means the microstructure. So this is one type of research. Right now, this thing is going on. Same like cold rolling, there is another thing called side rolling of WAAM. So what is the difference between cold rolling and side rolling? In this cold rolling, they are rolling over the surface, but in side rolling, they are just tilting the component. They are rolling on the sides of the component. Here. So they are rolling on the side of the component. So this is the only difference between cold rolling and this side rolling. In cold rolling, they are not getting the pure surface finish, but in side rolling, they are claiming the surface finish is good. So this is another methodology of another research area. Now thermoelectric cooling setup. What happened actually? What they are doing? You can see same wall. There is no difference in the wall. In the wall, they kept a fin-shaped structure. You can see this fins. Actually, this type of fins are available generally in the PCB boards. There is a fan. So what they are doing, they are sucking out the heat using the fan structure and fin structure. What will happen? This will allow to uniform distribution of cooling in the. It means this will allow the entire system to cool down steadily. So the repeated heat cycles, it will help to avoid that cooling. So this will help to improve the component. So these are the setups also right now people are just attempting. They are not working much on it. Then combined cooling process. In this combined cooling process, see, same. What happened here? They are introducing some setup. In this setup, they are trying to suck out the heat. But what here they are doing, generally welding comes with a shielding gas that everybody knows. Now they are using another gas like CO2 gas. What this CO2 gas, actually generally we will say CO2 gas as a dry ice. So that dry ice gas will be flown over the surface. It will remove the heat, means it will cool the surface. So this is the another area of research. They are attempting to do this cooling setup. This is one area of research. Actually, there is no proper outcome of all these ideas. People are still working on this type of research, and this is one of the process. And induction heating. See, right now what happened in these things, people are trying to suck the heat out, means cooling or these are used to remove the heat. But what is happening in the welding? It is heating continuously. So what in this idea they are trying induction heating, why to suck out the heat, we can maintain the uniform heat. Means welding is a single point heat source, means one point only heat is there. When we are maintaining the single point heat source for a little longer time, the repeated heat cycles will reduce. So they are thinking to produce the induction heater. That induction heater is used to maintain the weld pool area. It is a kind of concept that is used for heating the base plate, because in the base plate, as I already explained you, base plate is around 30 to 40 degrees Celsius. If your deposition is 1000 degrees Celsius, there is a huge heat difference. It will make your base plate to bend or many other stress related activities. The same concept what they are doing here, they are doing it for only particular location of this welding area, means this bead area, that will help you to reduce the heat in the component. Then another thing is hybrid process. In hybrid process, in the previous process, everything only deposition is there. But in this hybrid process, one layer is deposited. Actually, what will happen when you are doing for a weld bead? The weld bead is kind of a dome shape. It will affect the next bead because of this. When during the deposition stage, liquid metal is in the liquid stage. Any liquid will behave the fluid form during its deposition, because it's a gravity, it will behave like a fluid only. So if it is in a dome shape, if you put a liquid over the material, that will try to slip down, but it is not huge, it can be controlled. But the thing is, it also behave like that. So what they are doing is, right, they are doing in such a way, the previous layer means 1/3 of the dome is removed by machining. Again they are going for deposition. What they are claiming, actually this work is claimed that it gives more of material integrity, and the deposition strategy was means the post monitoring and other things are working better with this type of hybrid system. So already this system was quite established, and people are right now migrating in many government organizations for this hybrid process. It means it can be well monitored. So this is one type of research. And pneumatic hammering. Pneumatic hammering is, I think you have in the first image you can see that actually we will hammer it on the component to get the shape. The same way what they are doing, the pneumatic hammering with the fixed cycles and frequency, they will hit on the component. That component will continuously means hitting, means it's, you see the image. See, in this image, when you are applying this cold rolling is a continuous contact. It is giving continuous pressure on the complete wall. But pneumatic hammering, the same, it will follow the path with the repeated cycles. So when this type of repeated cycles are happening, it will help us to remove the residual stress to ensure the component quality. So people are doing in the pneumatic hammers way ahead. Right now people are in some machines, they are using with laser peening also, means laser energy is used to hit on the surface, and they are doing, and the same thing happening in water jet peening also. This peening is a common operation, so that we know if you are hitting on a surface for some extent, the stress will be removed. The same thing can be applied for water and laser. These things are doing. So overall, up to from cold rolling, side rolling, thermoelectric cooling, combined cooling, induction heating, hybrid process, pneumatic, water jet peening. All these things are completely research areas. There is no much data about it. Means only the process was discussed. So if you able to attempt this area, these areas will give them yield in a short span of time. So overall, this, I think the slide is able to visible. Kindly check into the summary, and if you have any doubts, please ask. Start your questions. Thank you.
Participants can ask your questions. Sir, I have one question. Shall I
Yeah,
ask?
please, sir.
So, can we use some other non-ferrous metals like magnesium or zinc through this wire additive manufacturing?
Sir, actually, wire additive manufacturing has a flexibility. If you are able to get the welding wire, any welding wire can be used for wire arc additive manufacturing, sir.
Okay, okay, thank you, sir.
Even inconel, monel, aluminum 40 series, 60 series, stainless steel 316, 304, even stellite. I think stellite is the hardest material. So almost everything, any material that can be available for welding or wire form, that can be used in wire arc additive manufacturing. There's a freedom for working with any material. Even in
Sir,
few cases, yeah,
finish, sir, finish.
yeah. Even in few cases, people are developing their new alloy. They are doing ingot. They are drawing into a wire, and they are doing their studies. So you can do any material. That is not a restriction for wire arc additive manufacturing.
So, what is the microstructural difference between the wire additive manufactured component with the same material with the powder additive manufactured components? Sir, any microstructural difference will be there?
Sir, no, sir. They're both are same only because both are operating under the same temperature because it's the melting temperature of the metal. So both are same only. There is no much difference. The only difference is wire arc you can go with meter size component, means very big component. But when it goes with this powder based, you have to go with micron size component, small size component. That is the difference.
Okay, sir. Thank you.
Yes. Anybody else, sir?
Sir, this is Vetrichalan, sir.
Yeah, please wait it, sir.
Sir, can we make 8000 series aluminum? Actually, I'm in a proposed, I'm in a research in doing 8000 series composite materials, sir.
Okay, sir.
Mixing silicon carbide with aluminum 8000 series. Is it possible to do it with wire arc welding, sir?
Sir, we can do it. Kindly have an inquiry about whether 8000 series wire is available in the market. I hope it must be available because we are using 4000 series and 6000 series.
Okay.
Even magnesium alloy series also I use, means SiMg alloy wire. I am not sure whether 8000 is available, but I hope it is available definitely.
Okay, okay, sir.
Do little local market survey, sir.
Okay, sir. Okay, thank you.
Anybody else, sir?
Sir, I think there is no more questions. So,
Okay,
shall
sir,
we
then-
proceed for next?
Okay, sir. Then I think thank you for the opportunity, sir.
Yeah,
Sir.
we profusely thank Dr. Manivannan for his very informative and educative lecture. He covered widely both the powder technology and the wire arc method. So it was very informative and educative. Thank you very much, sir.
Thank you, sir. Actually, if anybody further interested in research, you please contact us. We will help you doing this research works. Actually, these are undeveloped areas, and people are not touching these areas in a wider manner. Even in foreign countries, actually, these companies like Siaki, Arcam, they have developed their electron beam based things. Means when you are saying additive manufacturing, people are working in laser based thing, but people are way ahead than India. So when we can able to achieve this in like our normal arc based things or plasma based sources, then we can easily achieve this our Atmanirbhar or Make in India this schemes. So this will be good for the researchers or entrepreneurs.
Okay, sir. Thank you very much.
Okay, sir. Thank you, sir. Thank you for the opportunity, sir.
The valedictory function will start in a short while. Participants, please continue to stay.
Sir, I think we can directly move on.
I now invite Vice Principal cum Dean of Academics, Dr. S. Matilda, to deliver the valedictory address. Over to you, Dr. Matilda.
So, can you hear me? Is my voice audible?
Yes, ma'am.
Okay. So, a very good evening to all of you present here. And I take this opportunity to congratulate Dr. Ganesha Balamurugan and the co-coordinator, Professor Santosh Kumar, for having chosen such a topic which is almost close to my heart. So, the reason being, and I was attending Dr. Manivanan's session right from the beginning, and it was such a wonderful session. So he was stressing on so many things which I actually wanted to tell. But let's go way back, say 20 years back or even now. What is happening in the production environment? I think all of you as mechanical engineers will be better equipped with an answer. Right, you need for actually producing, let us say, even a small part or an automobile part, let it be, or some other machine part. What we need is at least 1,000 square meter space, right? And machine, starting from your shearing machine, you need your press, you need your lathe, drilling machine, grinding, everything. And after post-processing, you need this electroplating and all this. Is it clear? So a minimum 1,000 square meter area plus all these machines. And once you walk into, generally we'll say it's a workshop, right? So how you can imagine, as well imagine how a workshop environment will be. You'll be having all the waste strewn around, greasy things, all your machines will be greasy. You cannot expect that sophisticated environment which a computer science or which a software engineering is venturing for. Now, but things have changed, right? The core engineering branches, they still have this stereotype idea telling that this is how a production environment is there even today, right? Might be, let us say, even 50% of the production environment is there, but it is only in a low scale environment that is still existing. But when it comes to mass manufacturing, things are moving at a faster pace. Right now we are moving toward alternate methods of production. For example, keep on one side the production environment which I described, and now all these machines can be replaced by a simple 3D printer in an AC environment in just 200 square feet. I told square meter there, it is square feet area in an air conditioned room. Just like any software engineer, you can sit and do your work. So this is so amazing, but it is still to reach the students, or it has not reached the next generation. So I think it is first and foremost our duty to carry this to the next generation, telling that it is not that production environment which you saw, and things have changed way ahead. So studying mechanical is as good as studying any software engineering course, your computer science engineering course, your artificial intelligence, name anything. Everything has come into your, this core department. And the second thing we face generally, all of you might have faced, for skill related jobs, the number of people available is on the decrease. For example, getting a plumber or a lathe operator, a turner for that matter, it's very difficult these days. Even a few years back it was difficult, and today it is all becoming, slowly it is moving away, right? All these skilled labor, people feel it is much below their dignity to do it, so that skilled labor is still in demand. But again, for that also there are alternate ways or alternate operative methods which are falling in place. So as faculty members, now one thing I request you is carry this difference, or how your particular domain or department or your area has changed from what it was, what it used to be, to what it is now. This awareness, it need to be created among the students so that they are encouraged to join the core courses. And once upon a time, I remember people will tell Royal Mech or mechanical is an evergreen subject. It is still evergreen. Thing is, we are not nourishing it. That's why it is not flourishing. That is what I feel. For example, the subtractive manufacturing, which I told earlier, has turned into your additive manufacturing, which is clean now, no waste material. no greasy hands and other things. And plus, this is still developing, as Dr. Manivandan rightly told, it is still developing. So there are ample avenues where you can venture into and do your research. You can also involve your students. You'll find the amount of interest they will show when you're going to do it in person, or when you're going to demonstrate a 3D printer. You can see, because we had that experience 2 batches back. Students assembled their own 3D printer and they were so excited. It is like, they were gifting all the faculty with their initials, that the keychain with their initials and all that. So this is how you can take things to the next level and make your department more attractive to the general public as well as the next generation. So, and one more request to all the faculty, what I usually say only, see, please don't stop with this. Like, 5 days I came here, for 6 days I came here, I heard some lectures, I'm getting a certificate, but when I'm going out, I'm going back empty. That should not be the case, right? Please carry with you something, some bit. One lecture must have struck you, or one point which a particular professor told would have created a change in you. Please carry that with you and carry it down to the students. And today, as such, classroom teaching alone is only 30%, whereas we are supposed to do lots of research. Earlier, they used to bifurcate research and teaching and all that. Today, that's not the case. People, teachers like us, unless we learn new things, we cannot carry it forward to the students. So equip yourself with the latest technologies and find avenues where you can do something better than what is existing today. The production environment which existed has been changed, has found a drastic change. So this is because of someone's research. Same way, there is ample scope here, like Dr. Manivandan told, the material which we are using, there is a limitation. The cost, there's a limitation. The time, again, there is a limitation. So many areas are still are there which is not which is untrodden. So my dear faculty members, please look out the avenues where you can do a simple environment, publish your work, and see that you gain more knowledge and you get deeper into research. So one thing about this core engineering is, see, in computer science you cannot see all the zeros and ones, you cannot see the voltage. Am I right? All of you would have felt. Whereas what you people do, people can see physically, so the appreciation is there directly than running a software program and getting the result. Once I see the result, I don't know what the machine did, I get the result. But here in 3D manufacturing especially, you will see inch by inch how your product is developing. Okay, so that gives more happiness than running any program or writing a software code, a piece of code which is going to do something. Is it clear? So be proud of your department, but ensure that this pride, along with this pride, you carry on what is actually there in your department to the next generation, so that we as engineers can flourish and we can make the world a better place to live in. Thank you one and all. Thank you so much.
Thank you very much, madam, for your thought-provoking speech. The writing on the wall is very clear to us. You have addressed the revolution taking place in the manufacturing technology, and we understand that it is our duty to carry this message to the students and to the all prospects who are aspiring for engineering. We will definitely take this as a job to be done. Thank you very much, ma'am.
Sir, excuse me, this is Manivandan.
Yes, please.
Yeah, sir, actually, kindly give me a chance to express my things in this regard.
Please.
Actually, ma'am said is really a great thing. Actually, all her words are completely become the experience. Right now, ma'am said this 100 square, 1000 square feet area, all these things are really, we are also facing the same issue. Right now, things are completely moving in the way where ma'am is saying. So it's as behalf of ma'am, I am also requesting you people, so kindly go into this research area so that this will helpful for you and the same way to the country. So it's really nice, ma'am. Nice to meet you, ma'am.
Thank you so much, sir. Thank you.
Thank you.
I think we can now move on to the vote of thanks. I request Professor Santosh Kumar, co-coordinator of this program, to propose the vote of thanks. Over to Mr. Santosh Kumar.
Thank you, sir. Good evening, everyone. Honorable Chairman, Mr. K.V. Raja, Secretary, Mr. K. Shivaram Alva, Treasurer, Mr. R. Vimal, Principal, Dr. G. Magendran, Dean Academics and Vice Principal, Dr. S. Matilda, professors, faculty, and students of various universities and institutions, and my colleagues. It is my privilege to extend a hearty thanks to everyone on behalf of the Department of Mechanical Engineering of IFT College of Engineering. Feeling thankfulness and not expressing it is like wrapping a present and not giving it. Today, I take the opportunity to put all our gratitude into words. I express my gratitude to the resource person of this program, Mr. Kumar Ramajayam, CEO and President, Bison Bots Labs. Mr. Anand Kumar Mishra, Operation Manager, 3 Dexter Education Private Limited. Dr. Mamila Ravishankar, Associate Professor, Department of Mechanical Engineering, IIT Tirupati. And Dr. Manivannan R, Scientist, Wire Arc Additive Manufacturing and 3D Printing, Center for Additive Manufacturing and Metrology Group, CME-RI, for enlightening us and enriching our knowledge. I extend my sincere thanks to our beloved chairman, Mr. K.V. Raja, for his constant guidance. I heartily thank our secretary, Mr. K. Shivaram Alva, for encouraging us. I also thank our treasurer, Mr. R. Vimal, for his gracious support. I thank our principal, Dr. G. Magendran, for providing us counsels. I express my thanks to our Dean Academics and Vice Principal, Dr. S. Matilda, for your guidance and help. I express my sincere thanks to our Head of Department, Mr. V. Velmurugan, for his encouragement. I also thank coordinator of this program, Dr. K. Ganesha Balamurugan, for his constant support. My hearty thanks to the organizing team. Last but not least, I thank all the faculty and students of various colleges for showing interest in the program and for the participation. Thank you, one and all.
Thank you, Professor Santosh Kumar. We have come to the end of the CSIR sponsored online 2 days national level seminar on challenges and opportunities in 3D printing and design. Hope all of you enjoyed these 2 days of intellectual stimulation and nourishment. Thank you, everyone.